Okay, so let's get started. Today is going to be a bit more of a fun tutorial. We're not going to be looking at proving series or conversion or things like that, but we're just going to have fun with series and sequences, and we're going to look at different interesting applications that they have. So since you guys are learning about Taylor series this week, I didn't want to pick something that was heavily involved in using a Taylor series to solve something, for example, just because you guys are simply digesting the information right now. So instead, we're going to be looking at some other things, still related to series and sequences, though. And the first problem that we're going to work on is called the leaning tower of light, also known as the block stacking problem. So let's start with that one. Okay, so the block stacking problem is pretty simple. The objective is to make a tower of blocks that extends as far as it can horizontally off the edge of a table without tipping over. So, for example, if you have one block, then it can be in three different scenarios. It can either be in a stable scenario where it's definitely not going to tip over. Then it can be in a scenario where definitely is going to tip over, and then in one situation where it's like just on the edge of tipping over. And just to make our life simpler, we're going to assume that the blocks are of uniform density, everything's uniform about them, they're square and everything, and they have a length of 1. So if I want the block to not tip over off the edge of the table, what should the gap between the right-hand edge of the block and the edge of the table be? Yep, pretty simple. It should be 1/2. And the idea behind that is that we want the center of mass of our stack of blocks, in this case one block, to be right above the edge of the table. So if you want to figure out how far this kind of overhang of the blocks is going to be for n blocks, let's say, we're going to do that using induction. So let's assume that we're in a situation where, I guess I'll draw it here first, that you have a stable configuration of n of these blocks. So this tower isn't going to tip over, you have a stable configuration of n, and the center of mass of this block is, let's say, is on that dot somewhere. Horizontally, it's on that dot. Now, if I want to place this on the n+1th block, so we're going to put this entire stack on top of another block, then if I want this stack of n blocks to not tip over, basically the center of mass has to be within has to be just at the edge of the last block. So in this case, the stack of n blocks is going to tip over. So now, what does that tell you about the kind of like, let's say it's something like that. It's not that good of a drawing, but you get the idea that the center of mass has to be just at the edge. What does that tell you between? What does that tell you about the gap between the center of the bottom block and the center of mass of the n blocks placed above it? Well, it tells you that they have to be at a distance of half again, because this is basically just at the edge of the block at the bottom. And we're going to place this entire stack of n+1 blocks onto this table over here. Now, what we want to find is this distance over here, that is the change in the overhang. So we can call that change delta. So before we had a stack of n blocks with a certain amount of overhang, and then by placing another block underneath it, we were allowed to push the tower slightly further, and that change in the total overhang is what delta is. And basically, the way that we balance the entire system is that we want the center of mass of all of these blocks, so the n+1 blocks, to be placed right at the edge of the table. And we can actually figure out delta using that. And for that, I'm going to use kind of like a moment balance equation. So let's say that you have a little beam. Here's a pivot. And then you have the weight of n blocks on this side. And you have your weight of a single block on this side. It's kind of like what you're doing over here, trying to find the center of mass of the entire system. And you know the gap between the center of mass of the bottom block and the center of mass of the end blocks is 1/2. So this entire distance is 1/2. And the distance between the center of mass of the system, so basically where the pivot is, to the center of mass of the end blocks, which over here, is equal to delta. So therefore this distance has to be 1/2 minus delta. So 1/2 minus delta. And then you can just do force times distance for both of these to kind of balance the beam, right? So you have force times distance, force times distance. So the force is 1 and the distance is half minus delta. And the force here is of n blocks and the distance is delta. And now you can solve for delta and you'll get that delta times, let me just think about this. This half minus delta equals n delta, and then n+1 delta is a half. So delta is equal to 1/2 times n+1. So this is the change in the overhang after you add one more block into the system. So we know what the overhang is with one block. It's equal to half. So the overhang for 2 blocks is equal to the overhang for 1 block plus the change in the overhang. So plus 1/2, and in this case, n is 1, so we have 1 plus 1. So that's equal to a half plus a quarter. And then similarly for O3, it's equal to O2, which is a half plus a quarter, plus 2 and 2 plus 1. So you get a half plus a quarter plus a sixth. And then you can imagine that you can keep on going for other overhangs and such. So does anyone see what theories this is following? I might make it a bit easier. You can say it's half times 1/1. Yeah, exactly. It's a harmonic series, right? 1/1 plus 1/2. And then this one is a half times 1/1 plus 1/2 plus 1/3, and so on. So this is just a harmonic series that is multiplied by 1/2. So the overhang for n blocks is the sum from I equals 1 to capital N of 1/2 I. And what do we know about the harmonic series as n approaches infinity? So basically, O infinity equals, yeah, it diverges, right? and it goes to infinity. So what this tells us is that if you have perfect blocks, you could basically stack them infinitely high and infinitely far along without them tipping over. That's pretty neat. I actually wanted to show a demonstration with like a couple of blocks just to overhang by one entire block. So the block at the uppermost layer is completely over the base, but I couldn't find any Jenga blocks at home. So do we have any other questions related to the process I described over here? So this was just like one of the interesting things I wanted to talk about today. Okay, then I guess we can move on to the Fibonacci numbers. Now, Fibonacci numbers by themselves aren't all that interesting unless we decide to do some interesting things with them. So generally, the way that they're defined is that you start out with two numbers, let's say 0 and 1, and then the next term is basically just equal to the sum of the previous two terms. So 0 and 1, add them, you get 1, 1 and 1, 2, 2 and 1, 3, 3 and 2, make 5, 3 and 5, make 8, and so on. So the recursive formula, so the n plus 1 Fibonacci number is equal to the nth Fibonacci number plus the n minus 1 Fibonacci number. So we've all seen this. This isn't something new or anything. But something that we don't usually look at is we can actually extend this system to count in the negatives as well. Right? There's nothing stopping us from going that way. So what number plus 0 gives me 1? Well, 1 plus 0 gives me 1. And then what number plus 1 gives me 0? And that's negative 1. And then what plus negative 1 gives me 1? That's 2. You get negative 3, 5, negative 8. So yeah, so you can extend the Fibonacci numbers into the negatives, and then what you'll see is that it's actually the same magnitudes, it's just that the sign keeps flipping every single time. And maybe I can, so this is Fn, and then we have n over here, so n is 0, 1, 2, 3, 5, 6, negative 1, negative 2, negative 3. So now the natural question is that, okay, we have this recursive formula that I can use to calculate f to the, sorry, the 8th or the 10th or the whatever Fibonacci number. But for me to calculate the 8th or the 10th, I need the Fibonacci numbers before it because this is what the formula requires, right? So the next thing to ask is that, is there any general formula to the Fibonacci numbers? Like, given a value of n, and without needing to calculate all the previous Fibonacci numbers, can I figure out what the nth Fibonacci number is? And there is a formula for that. It is actually called the Binet formula. So it's 1 over root 5. And let me just make sure I copy this off right. That's 1 plus square root of 5 over 2 to the power n minus 1 minus square root of 5 over 2 to the power n. And you can try out a couple of numbers. If you plug in 0, you'll get 0. If you plug in 5, it'll give you 5. If you plug in the negative numbers, you actually get the negative Fibonacci numbers exactly like how they are over here with alternating signs. So we started out with the Fibonacci numbers being just positive integers. we've extended it to include negative integers. Now the next kind of question to ask is there any way I can calculate the half Fibonacci number? Like, is there anything between 0 and 1 that I can calculate? Like, what does it even mean to take the half Fibonacci number? Okay, like, what happens if I put n equals 1 over 2 into this formula? So f of 1 over 2, this is already kind of questionable. What is this? It is 1 over root 5, 1 plus square root of 5 over 2 to the power half minus 1 minus square root of 5 over 2 to the power half. And now things to the power half are just square roots, right? So I can just do square root of this. Does anyone see any problem with this so far? Like, sure, I can compute 1 plus square root of 5 over 2 and take the square root of that, that's fine. But what about this, 1 minus square root of 5 over 2? Well, this number is actually negative. So, yeah, this is a negative number, and we take a square root. Exactly. That's going to give us an imaginary or a complex number, right? So let's say that that's allowed. Let's say that we're allowed to put in non-integer values and they spit out complex numbers. So now, how do those complex numbers kind of, like, what shape do they describe? Like, how does the path between 0 and 1 transform when you put it through this formula? So we're basically looking at something called conformal mappings for complex numbers. And it's to do with trying to visualize how these functions map the input space into the output space. And to kind of get a small understanding of that, we're going to watch a part of a YouTube video that kind of demonstrates that really well. And then we'll apply it in this situation and see what happens. So let me just share my screen. So can you guys tell me if you can hear the audio when I play this video?
Out of dimensions. Fortunately, there are some very clever ways to see
Okay, so let's watch this.
the relationship between two complex variables. But before we can get to these, we need to think about the mathematics of complex functions. Even though using separate planes for our input and output is not a perfect solution, this approach can still help get us started. Let's try it out with our original function, f of x equals x squared plus 1. Before we begin, let's make a quick variable change to make things easier down the road. We'll change the name of our input variable from x to z and call our output variable w. Since z and w each have a real and imaginary part, let's go one step further and give these parts names. We'll let z equal x plus iy, so x represents the real part of z and y represents the imaginary part. We'll also let w equal u plus iv. Just as we can use tables to keep track of our inputs and outputs for real valued functions, we can also use tables to keep track of our inputs and outputs for complex functions. However, we now need 4 columns to keep track of our 4 variables, x, y, u, and v. We can now experiment with our function f of z equals z squared plus 1. If we plug in a complex number to our function, for example z equals 1 plus I, we can do a little algebra and obtain our result, w equals 1 plus 2i. Plotting our inputs and outputs, we see that the point 1 plus I in our input plane was pushed or mapped by our function to 1 plus 2i in our output plane. Let's plug in a few more points here and see if we can find a pattern. If we test points along a straight line in our input space, we see that in our output space, our straight line is transformed into a curved line. Interesting. As you can imagine, plugging in points like this can get pretty tedious. To speed things up, let's let a computer do it for us. And instead of having our computer just map certain points, let's have it map all the points. We'll take advantage of the fact that the image you're seeing is just a collection of pixels that happen to be arranged on a grid. We'll use some code written in the programming language Python to move every single pixel in our input space to its proper location in the output space. To make this work, we'll assign each pixel in our input video a complex number that corresponds to its location on the complex plane. We can then let our code take care of the tedious work of moving each pixel to its new location, as dictated by our function, z² + 1. Our code will move points exactly as we did by hand before. If we have a blue pixel at the 1 + I location on our input graph, then this blue pixel will be moved to the 1 + 2i location on our output graph, because f of 1 + I is equal to 1 + 2i. We saw before that our function warped a straight horizontal line into a curvy one, so it should have some interesting effects on our video. We'll include some reference markers on top of our input and output planes to keep track of our numbers, but we won't transform these pixels. All right, ready? Let's start by drawing some simple lines. A horizontal line along the positive x-axis turns out to be something pretty similar in our output space. But what about a line along the positive imaginary axis? This line appears to have been rotated. As we add more lines, we begin to see a pattern. Our family of straight lines is turned into a family of curved lines. Cool, right? So we found one pattern, but how is this pattern explained by our function z² + 1? And more importantly, how does this fit with everything else we've learned about complex numbers? What else would be interesting to draw in our input space to test our mapping? What shape would you draw to learn more about what our function is doing? Next time, more shapes.
Okay, so that basically kind of explains how conformal mappings work. And what we're going to do is use our function, our Fibonacci function, and see how the complex plane transforms under this. So let me share, actually I am sharing right now. I'll open up my MATLAB where I've been calculating this stuff. So you can see that I'm just applying our formula. So our xd is our discrete variables. So that's -5 to 5. And we're going in increments of 1. And then our Fibonacci numbers are stored right here. So you can see that the 0th Fibonacci number is 0, the first Fibonacci number is 1, the second Fibonacci number is 1, the third Fibonacci number is 2, the -5th Fibonacci number is 5, and so on. And then I did the same thing. I used the same formula, but instead of x being just integers, I actually took kind of like a linearly spaced vector between -5 and 5. So we have decimal values as well in there. And as expected, when I put this to the function, it spits out complex numbers. And you can see that this is a real part and an imaginary part. So let's look at how just the discrete points move in our plane. So if I run this, you can see that that's probably going to take a second to run. You can see that the point that starts out at 0 stays at 0. And then let's try and track some other values as well. So the point that starts out at 2, because the second Fibonacci number is 1, should move to 1. So if I run this animation again, you can see that the point from 2 moves to x = 1. Similarly, the Fibonacci number for x = -5, the Fibonacci number is 5. So you can see how that point that started out at -5 just zooms across the axis to approach our value of 5 over here. So points that are integers stay on the real axis. But what happens to the non-integer points on the real axis? How do they get mapped onto the complex plane? And I will show that using, if I run this, you can see how the real axis transforms based on, because some So like initially these points were all on the real axis, but after passing through our function to calculate the Fibonacci number, they take complex values, and what we're plotting is their location on the complex plane now. And this shape is pretty much what you find on the beach, right, in shells and things. So I just decided to put a picture of a shell underneath the plot and kind of see how well that fits. And you can see how satisfying that is, that it nearly fits the shell perfectly. Some interesting things that we can see is, for example, over here, or wait, let me just hide the shell again so I can zoom in properly. Some questions, okay, no questions, just reactions. So we let this transform. So what are the first Fibonacci numbers that start from 0? So we have 0, 0 stays on 0, and then 1 maps to 1, but then the second Fibonacci number also maps to 1, hence we see this small loop over here. So we go from 0 to 1 again, and then to 2, to 3, and then to 5. And when we go in the negative direction, you can see how that spiral works, right? So from 0, we go to 1, then we go to -1, then we go to +2, then we go to -3, then we go to +5. So it's kind of spiraling the other way around. And the spiral is needed to alternate between the negative and positive numbers that you see for negative integer values of the Fibonacci series. So do we have any questions related to what we just saw? Something like, I know I just dropped a lot of knowledge right now related to conformal mappings and complex functions. If not, then I can go to our third topic of the day. So let me find the page where I wrote this stuff on. Okay. Now we're going to look at one of the most common problems that you see in physics, and that is modeling the simple pendulum. So let's say that you have a pendulum with length L, you have a mass attached to that string, it's in a gravitational field G, and you want to describe the motion of this pendulum. So the force acting on the pendulum due to gravity is mg, and I guess now we can just apply Newton's second law, right? So you have F equals ma, but in the rotational sense, your forces turn into torques, your mass turns into your moment of inertia, and your acceleration turns into your angular acceleration. So what is the torque that this force mg imposes on our kind of system? So we can calculate the component of this force that is perpendicular to the string. So that is mg sine theta. And so this torque is basically mg sine theta, which is force, times distance, which is L. So it's mg L sine theta. And since we're measuring theta in the positive direction as counterclockwise, and this force is in, this torque is in the clockwise direction, so this is going to have a negative sign in front of it. For the moment of inertia, whenever you have a mass at a distance L from the center of rotation, the moment of inertia of this mass is equal to mL squared. And then alpha is basically just the second derivative of the angle, right? So you have theta, you differentiate it, you get the angular velocity, and then you differentiate again, you get the angular acceleration. theta double dot. And then we can just cancel a bunch of stuff and rearrange. So theta double dot is equal to minus g over L sine theta. And then what is the key step that nearly every physics textbook takes to solve and obtain the equations of motion for this situation? There's an approximation that nearly everyone makes. Yeah, everyone just takes a small angle approximation, right? So hopefully all of you by now know about the fundamental theorem of engineering, which is that sine theta is theta, cosine theta is 1, tan theta is theta, and that pi equals e equals 3. So that's your fundamental theorem of engineering. And if you apply this, you get that the second derivative of the angle is equal, or is approximately equal to minus g over L theta. And that's basically the equation of motion that everyone tries to integrate to find how theta varies with time. So we're going to do something similar in MATLAB where we're going to integrate this function. And so what am I integrating? Well, in this case, since this is a second order differential equation, you see you have theta double dot here. What we have to do is we have to track two variables. So we're going to be saving the angular position and the angular velocity of the system. So this is called the state. And we have access to both of these variables, okay? So now let's say that I want to compute the derivative of my state, right? So the derivative of theta is theta dot. The derivative of theta dot is theta double dot. And now these have to be functions of my state. Well, I already have theta dot, so I can just use that again. And theta double dot is just equal to minus g over L sine theta. So minus g over L sine theta. So this is our kind of our actual derivative. Our approximate derivative using what we have over here is theta dot, and then you have minus g over L theta. So where you kind of approximate sine theta with just theta. And then what if we want to try something that's a bit more accurate than just using theta? Well, we can just use the Taylor expansion for sine and substitute that in. So let's say you have sine theta is equal to, so the Taylor expansion for this is minus theta cubed over 3 factorial plus theta to the 5 factorial minus theta to the 7, and so on. So this would give me a better approximation than just this. So what we can do is, instead of just theta, we use the Taylor series expansion. So you have theta minus theta cubed over 3 factorial plus theta 5 factorial. And we can truncate that to whenever we feel like we have the desired accuracy that we need. So in my MATLAB code, I've called this the actual derivative, and this one, call it the simple derivative because it's pretty simple. And this one, we can call this the approximate. So let me hop onto MATLAB and just walk through the code on simulating a system such as this. So this is our, let's say our initial condition is that, so our state vector, remember it was two variables, our theta and our theta dot. So the initial condition of the system is that that theta is equal to 10 degrees and that theta dot is equal to 0. So you basically, you move the pendulum 10 degrees and you just let it go. And this is just my integration. I'm going to be taking steps of 0.001 seconds, and I want my simulation to be 30 seconds long. And then here are my derivative functions. So you can see that the simple derivative is just equal to, so remember x2 is our angular velocity. So yeah, the derivative of the angle is the angular velocity. And assuming g and l are 1, the angular acceleration is just minus theta, so it's minus the angle, which is x1. Our approximate derivative was using that Taylor series expansion. So we have, how many terms is this? 1, we have the x cubed term, and we have the x to the power 5 term. And then the actual derivative is when we calculate the sine of our angle. And this is just a simple Euler integration scheme. So for example, if you have the state in the current time step, then, and if you want the state in the next time step, you just take the derivative and you multiply it by delta t. So basically, like x2 is equal to x1 plus x dot times delta t. And then you just keep on doing that. Are we assuming G over L equals 1? Yep, that's our assumption. Just assume everything's 1. G, L, M, not theta. Theta keeps changing. Okay, so once we have this, I guess I can just run this, and let's look at a plot of the different outputs. So the upper plot is the angle, and the lower plot is the angular velocity of the system. And then there's supposed to be 3 lines, but they're like basically right on top of each other. You can see a bit of divergence in, like, as the simulation progresses. So you have the blue line is the simple, so just the angular acceleration is equal to the negative of the angle. And then you have the approximate one, in which we use the Taylor series expansion. And then you have the actual one where you say that the angular acceleration is equal to minus sine of the angle. And we see pretty good agreement, and that's simply because, well, we're starting at 10 degrees, so our small angle approximation is actually a pretty good approximation. So let's start pushing this angular value of, let's say we're at 40 degrees. So yeah, now we see a little bit more difference where the simple pendulum just follows some simple harmonic motion, and kind of like it diverges from what the actual system is doing. Maybe I can make the angle a bit more, let's say it's at 60 degrees. It still looks like simple harmonic motion. Let's crank it way up, like 120. So yeah, so you can see that when the initial condition is that theta is equal to 120 degrees, then the blue line follows simple harmonic motion, which is just as what it should. You can see that the actual pendulum doesn't follow simple harmonic motion. And it's pretty obvious to see that in the angular velocity, actually. That looks pretty, I'd say it looks like almost like a triangular wave. And now we also see our Taylor series expansions slowly moving away from the actual system because we're only taking a couple of terms. So let's make this even more. Let's go all the way up to like 170 degrees and see what the system looks like. So you can see that the actual system doesn't even match our Taylor series expansion anymore. And it's definitely not some simpler harmonic motion. You can see the yellow curve is a much more flattened type of sine wave thing. And the angular velocity is just, it's whatever, it's just doing its own thing. So I'm not happy with how the approximate solution is way off compared to the actual one. So I'm going to increase the number of terms in my Taylor series expansion and see if that makes everything more accurate. So here is the Taylor series expansion. My last term was x to the power 5 divided by 5 factorial. And then, okay, so let me add the x to the power 7 term. And then, how about the x to the power 9 term? And what the heck, we're here already. Why not just add x to the power 11 term? Question, how does MATLAB calculate sine theta? It has a much smarter way that does not involve using a Taylor series expansion, because Taylor series expansions use a lot of computation, I guess. This is a lot more steps in a Taylor expansion, whereas there's much smarter ways to calculate the sine of angles. That's a pretty good question, though. So if I run the simulation now, so since our Taylor series expansion has more terms, it should be more accurate now. And that's exactly what we see. Actually, it's pretty much bang on again. And we can see that our Taylor series expansion matches the actual system dynamics much more closely. Now, to get a feel of how different the pendulums are behaving, I've actually made an animation of the 3 different derivatives that we're taking. So the pendulum on the complete left is going to be our simple derivative. So it's just theta double dot equals minus theta. And then the middle one is going to be our Taylor series expansion. And the one on the right is going to be the one where we say that theta double dot equals minus sine of theta. Yeah. So if I run this, you can see how the different pendulums behave. You can see that the simple one just doesn't spend enough time in close to vertical as compared to the other ones, which kind of look much more realistic. Okay, so let me see. Would the pendulum get stuck if you set it to 180 degrees? Yeah, it wouldn't move, right? Actually, all 3 of them wouldn't move in this case. Or no, maybe, let me think. The first one would move. Only the last one shouldn't move, I think. Or even the second one doesn't move. But yeah, the first one's definitely broken. The actual one's pretty good, and the approximate one fails as well after some time because our Taylor series expansion isn't perfect. Actually, the approximate one just breaks. But yeah, you can see the actual one doesn't move, exactly what it should do. So do we have any questions with what we've seen today? Okay, so what about other stuff that you're covering in class right now? Are you guys all following along well with that? I think so. You guys are covering Taylor series. What else is on the syllabus for this week? Why did the Taylor one break at 180 for the animation? Let's see. Let me look at the graph. The graph never lies. I say it broke purely due to it broke due to the fact that our Taylor series expansion doesn't match the value of sine that well when it's close to 180 degrees. If you set it at 190, would it behave like a 170 degrees or would it move in circles? I believe that is a pretty good question. So let's see this. Let me set it to 190 degrees. Let's share the pendulum again. So 190. Okay, yeah, that doesn't make sense. The simple pendulum just starts out by rotating the wrong way. The approximate one breaks, and the actual one works a-okay. A really easy reason to see why that's the case is maybe if I show you the actual Taylor series expansion. This is the actual function, it's sine of x, right? And then this is the simple approximation, you're just saying sine x equals x. Let's say care about are between negative pi and x pi. So this is kind of like the range of values we want to work with, because you can imagine anything beyond this, you could just divide it by pi and take the remainder. You can see that this is not a good approximation of a sine wave for large values of x. But now let's look at our Taylor series expansion. So it was this, and then we subtracted x cubed over 3 factorial. So it's getting better already. And we added x to the power 5 over 5 factorial. So good, but still, see, it doesn't really quite match the values closer to x equals pi, which is why our simulation was breaking when we just started the system from over there. X to the power 7 over 7 factorial. That's pretty much bang on. Then x to the power 9 factorial minus x to the power 11 over 11 factorial. So you can see that our Taylor series approximation is pretty close to what a sine wave should be. Now the reason why our Taylor series approximation failed when we set x equal to 180 degrees is that, okay, sine of pi is 0, but even our Taylor series expansion evaluated at pi is not 0. It's actually like closer to minus 0.0004, which is why the pendulum actually started moving, even though the initial condition was set at theta equals 180 degrees. Okay, so any other questions? You'd be posting. Yeah, sure, I can post the MATLAB code. You guys can mess around with it, and if you guys find anything fun, then for sure let me know. All right, I guess that's it for today. I will see you guys, let's see, next week, in 2 weeks. I'll see you guys in 2 weeks. All right, take care, everyone. Stay safe. Goodbye.